All right, how's it going, everybody? We are here for day two of week six. Today we're going to be talking about general strategy for integration. Yesterday we looked at partial fraction decomposition. We saw that it was a very algebraic section. We didn't really introduce any new calculus concepts. Today we're really just going to talk about, how hard is integration? Is basically the question that we're asking. We've very much been answering that question over the last couple of sections here, and the answer is very hard. And that's always going to be the case. So we kind of want to formalize that here today, kind of look at some general strategies for integration, as well as, thinking about where our limitations are as far as integration goes. If you've read the section in the textbook, they talk about our strategies for integration, and then they talk about the integrability of general functions. I'm going to flip that around here and kind of talk about these two things backwards here. Um, so I would first like to talk about this whole, what kind of functions can we integrate? And the book asks a very generic question: can we integrate all continuous functions? And hopefully we're all pretty aware that the answer to that is no. And the answer to that isn't just no, but it's a pretty aggressive no. It's not even close. If you were to arbitrarily create a function with random components, there is next to no chance that it's going to be a function that we can actually compute the integral of. And so, while it is very important conceptually for us to think of integration and differentiation as inverse functions, unfortunately, that sort of says to me that they're like that. I don't know, that they're in some sense adjacent to each other or equivalent to each other in our abilities to manage them. And that's wildly untrue. Real quick, before I walk away from it, you should notice I have an asterisk sitting right there next to inverses. Remember that integrals and derivatives are not perfect inverses of each other. The plus c that we get out of integration, integrals are always giving us an entire family of functions, not just one unique function back, but they're incredibly close to being perfect inverses of each other. And so differentiation is something that we refer to as a one-directional operation. What we mean by one-directional is just because you can do the forwards direction does not mean that you can do the backwards direction at all. And it seems like it maybe should be the case, but it's very much not. So differentiation is a one-directional operation because it's very often the case that I can take the derivative of a function, but if I were to then hand you the derivative and say, hey, what's the integral of this? You might really seriously struggle to actually perform that computation. A much, I think, a better example, to me, the best example of a one-directional operation is multiplication. And I don't think that we think of this as being something that we can really only do one way. But the fact of the matter is, if I ask you to compute the products of 13 and 17, I am positive that every single one of us, even without a calculator, could do that in less than 30 seconds, right? Just do a little multiplication on paper. On the other hand, if I asked you to factor the number 612,701 into its prime factorization, even with a calculator, that's probably going to take you a really, 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 really long time to figure that one out. And that is a tiny number right there. That's only in the hundreds of thousands right there. It turns out that that number is actually 631 times 971. That would have taken you forever to figure out, right? So finding prime factors of things is a really challenging problem right here, finding prime factors. But multiplying two prime numbers together is trivially easy, right? So multiplying prime numbers is one directional. We can do the multiplication, but if you're given a number that's the product of two primes, even with a computer, it might be taking literal days to compute the prime factorization. Another one, a little bit more technical here, computation of MD5 hashes. When you download large files from the internet, that they know that there's always a risk that there was maybe some error in the download. So often what they will do is take either the entire file or a predetermined selection from the file, and they will compute what is called an MD5 hash of that information right there. In most simplest terms, these hash functions are going to essentially create a polynomial function using some of the information, and then using the rest of the information, create a number that's going to get plugged into the polynomial function, and the output is what we refer to as a hash. In this case, particularly an MD5 hash. And so when you download very large files from the internet, the way that your computer will verify that the download actually went correctly is it will take an MD5 hash of the file that you've downloaded on your computer, and it will compare it to a known correct MD5 hash from the source that you downloaded it from. And if those two MD5 hashes, just a number, match each other, then it's pretty much guaranteed to be the case that the file that you have downloaded must be in its entirety correct, even though it might be a multiple gig file, a huge file. MD5 hashes are just a single number, typically like a 256-bit number or something like that. Different hashes, different sizes. But again, representing a massive amount of information with just a single number. And so the point here is that, like, if anybody in the class wants the MD5 hash of my bank password, and you can for Wells Fargo, you're welcome to have it. And I know that it's zero risk for me to distribute it, because even the most powerful computers on earth are going to take on the order of years to work backwards to determine what was the value that was hashed to produce that value there. It's just not something that we can undo. And so that's why the way that your bank passwords work, whenever you log into your bank on your computer, when you create your passwords for your bank, the password at no point gets sent to your bank. There's never any way that your bank is actually saving your password. When you create your password on your computer will create a hash of your password. The hash of your password is then given to the bank, and the bank is only storing some form of computed value from your password. Every time you go to log into your bank, again, you type in your username and your login or your password there, and again, your computer is then going to perform the hashing on your end, on your computer, so your password never gets sent over the internet. It will send the hash to your bank, to Wells Fargo, and then it will say, hey, does the hash of what he typed in here match the hash of what you've got stored over there? And if the answer is yes, then you're given access to the account right there. So your bank password is never even sent over the internet. A computation happens locally on your computer, and the result of that computation is matched elsewhere. And it's because MD5 hashes, and there's a huge, and again, I keep on saying MD5 hashes, but in general, there's a broad family of these things, hashes in general, where you just can't go backwards. It's not possible to undo that information. So even if somebody was watching you, your internet signal there and got your MD5 hash, zero risk associated with you losing any valuable information right there. So it's important to kind of think that just because differentiation and integration are very closely related, they are inverses of each other. One is almost generally impossible, and one is generally mostly always possible. So they do have a major distinction in that setting right there. So the book then goes on to define elementary functions. An elementary function is any function that's made up of addition, subtraction, multiplication, division, or composition of all of our standard functions that we learn about in algebra class, plus a few extra. Polynomials, rationals, power functions, exponentials, logarithmic functions, trig functions, inverse trig functions. Pretty usually we don't talk about hyperbolic and inverse hyperbolic functions because they have fewer meaningful real world applications, but there's some pretty interesting things that happen with hyperbolic functions, but a little bit less direct application. So it's typically something that we, in a sense, leave off and associated with the algebra classes that we take out there. But the point here is an elementary function is essentially like any combined way that you can put these functions together here. And so the point is, in defining this elementary function, what we want to say is we can take the derivative of any elementary function, and even better, we're guaranteed that the derivative of an elementary function is another elementary function. So this is really giving us a guarantee on manageability of functions and applying derivatives to those functions. On the other hand, we are not guaranteed to be able to analytically integrate an elementary function and get back another elementary function. There's plenty of functions for which we can prove that the antiderivative could not possibly be an elementary function. And I'm going to talk about this word analytically here. Actually, maybe, well, give me 1 second. I'll come back to this analytically idea right here. This is sort of a modifier I'm putting right there, but not defining it. But give me a second on that one. And so in general, the book does another good job here of just listing some functions. None of these functions are super crazy. They're all pretty simple, relatively speaking. But all of these functions have been proven to not have an antiderivative that we can express with elementary functions. And that's, in a sense, disappointing. If these are functions that aren't too wild, it feels like these are things we'd like to be able to handle. And we can literally prove that it's not possible to come up with antiderivatives using elementary functions that are associated with any of these examples right here. And so, I mean, Gosh, like I kind of get this. Like that to me seems like, oh, okay, I guess I believe that that's kind of a little bit of a strange combination there, some trig and some exponentiation. But things like, the square root of a cubic function, like, man. And even better, if the plus one wasn't in there, then this would be trivially easy because this would just be then x to the 3 halves. Just adding in a plus one, just a little bit of a horizontal shift to the left by 1 unit suddenly makes this literally impossible, right? That's just, it's a little discouraging almost in a sense that it feels like things that seem simple should be simple to deal with, and that's what we've learned is that that's just straight up not true here. One that I find of particular interest, I've already brought this one up more than once this semester, is this integral of e to the negative x squared dx. The reason why I find this one in particular interesting is because of its association with probability. I know I've already mentioned this multiple times this semester, but this is the essential core function that is the probability distribution function associated with the normal distribution. So the bell-shaped curve out there that is associated with like all of the most important probability computations that are ever done is actually defined by a function for which we cannot compute the integral. And the worst part is that the area underneath the normal curve is equal to the probability associated with the events in the shaded region. So it's constantly a topic of interest that what is the area underneath the probability distribution function that's equal to the probability. We literally can't even do this process for the most desired probability function that there is, which is a little disappointing. Now, it turns out that there are ways that we can come up with an expression that gets us towards something that looks like this. So I'm going to come back now to this word analytically. When we say to find an analytic solution to something, that means to come up with like a closed form solution that's like a function, but essentially an elementary function or composition of elementary functions. It turns out that there is going to be a technique that's associated with performing this integration, but it's going to be associated with finding an infinite series, an infinite number of parts that we're going to add together to build a function that is representative of this. So let me take a little step to the side here and show you kind of what I'm talking about. This is some stuff we're going to see in chapter 11. In chapter 11, one of our topics is going to be Taylor series. And when we're talking about Taylor series, what we're going to see is that there are functions, for example, the sine function that you're looking at right here, where maybe you could kind of picture for yourself that it actually makes sense to come up with polynomial approximations to the sine function. You should see here that we've got a negative cubic function that's overlaid on top of the sine function. And this cubic function is doing an excellent job of approximating the sine function, at least from negative pi to pi. It seems that it does much worse elsewhere. Over here, the pink function is a terrible approximation of the sine function, but relatively near zero, it's doing a very good job. And it's got a description of it over here. And in fact, I just called this a cubic right here. But in fact, it looks like I think they're graphing a seventh order polynomial right here. A negative seventh order is what you're seeing with that pink one right there. But the point is, it is hopefully the case in general that we can take more and more and more powers of terms, and we can keep on building up appropriate additional terms, and that the more terms that we have, the higher powers of polynomial parts that we've added on, that we can get better and better and better approximations associated with the sine function here. And so what you're looking at here with this graph is saying, let's get all the perfect, the exact right polynomial parts up to the power of n, in this case. And what you're seeing happen is the more parts we include, the better and better of an approximation to the sine function that we're getting. It's doing a good job of approximating further and further and further out there. And so you might be able to imagine to yourself, well, maybe if we just keep on going infinitely and adding on more and more and more terms to the sum that you're seeing like right here, this is only a seventh order approximation. But if we just kept going forever and just kept on sticking on more and more and more higher order terms, it seems that conceivably we could come up with a polynomial representation of non-polynomial things, like sine of x, like e to the negative x squared, stuff like that. One of the things, I do want to show this, I don't ever want to show this and let people think that Taylor series are going to just save us from everything. There are some functions that will never find an appropriate Taylor series to perfectly match them in the long run. The classic example of this one is the natural log of 1 plus x. You can see that function here in black. But as you're watching this n value increase here, it doesn't really matter how many terms we take. There is never going to be a polynomial function that's going to perfectly match that natural log right there. So one of our major topics in chapter 11 is deciding what functions will will have a Taylor series that converges to actually being equal to that function. We'll find that sine of x does have one where we can say an infinite series is exactly equal to sine of x. We'll find that natural log of x does not have that same property. One of the major reasons for this, by the way, is because if we're trying to use polynomials to represent the natural log function, we know that natural log has a vertical asymptote at y equals 0, or in this case at x equals 0, and in this case at x equals -1, since this is a shifted function. But what we know is that a polynomial will never have a vertical asymptote. It's awful hard for us to imitate an asymptote in such a sense right there. So not everything's going to have a perfect representation, but here's what you can now imagine for yourself. This is the Taylor representation for sine of x. If we could somehow find a Taylor polynomial, a Taylor series to represent e to the negative x, then now it's just a polynomial. And we can always take the derivative or the integral of any polynomial representation. And so one of the techniques we'll see in chapter 11 says sometimes if you end up at a function that you have no technique to perform the integration, if you find the Taylor polynomial of that expression, it's now a polynomial that does the job of a non-polynomial, like a sine function or an exponential function. That then gives us the ability to do differentiation and integration, since we can always handle polynomial stuff out there. So Taylor series, super cool. It's sort of the common ground. Every single one of the families of functions that's out there ever, if we can come up with a polynomial representation for it, it's going to give us a lot more manageability to be able to do things with the representation of the function that we see. So when I say analytically out there, I mean we're still going to come up with a difficult roundabout maneuver to find an integral for e to the negative x squared, but it's not going to be direct. We're going to have to use a series solution rather than just analytically compute a integral like we've done for all other examples here. So I want to talk about this one a little bit more. I know I've brought this one up more than once. I'm going to kind of, in a sense, step away from that specific one right here. But let's look at some integrals that are related to this one and kind of see what we think about them. I mean, our question that we're asking right now is like, is it integrable? Could you do it? So let's look at some related ones and kind of ask ourselves these questions. Do we think that this is going to be something that we could possibly find an integral for? So the first one right here, I am thinking to myself, this looks to me like a crazy close representative of this guy. And we just stated, like, it has been proven that there is not an antiderivative for either of these guys right here. This is kind of our base case that we're starting with right here. And so I am anticipating, because I read the textbook, that we will not be able to perform this integration right here. The thing that I feel like I need, I feel like the x squared is screwing me up. I feel like I'd like to do a substitution with x squared, like a u equals x squared. But if I did that, then I'd have a du equals 2x dx, and I don't have that extra x part right there. So obviously, hopefully, if you're just looking at the screen right now, the reason I'm saying that is because we now look over at the second one. This x is actually a huge help to us right here, because now I have a component, x squared, and its derivative, or a constant multiple of its derivative, just x right there. So it seems to me like this is going to be pretty reasonable for us to do a u sub right here, which we'll do in a second. This guy right here, it doesn't seem obvious to me what we might be able to do here. I guess in this case right here, it doesn't feel like the u sub is going to help me, because if I pick u to be x squared, then I've got a u here and I've got a u here. But again, then du is going to be 2x dx. I'd need an additional x component there that I just don't have. And so I'm not sure about u sub. Integration by parts does not seem like a crazy idea right here. And in fact, I can tell you, I'm just going to cover up that squared on this x right here. This guy right here is like, I think this is like the first integration by parts problem that we did or something like that, x squared e to the x. But that extra squared on the x right there makes that a bit more of a bugger. But I think we'll at least try this with some integration by parts and see what we see. I'm a bit skeptical here, so I'm just going to go ahead and give this a question mark. This third one right here, this looks crazier, but I think that we should be not trying to judge integration by the craziness of it. We've seen some crazy things we can do, and we've seen some not crazy things that we can't do. So I think trying to judge these off the cuff is a bad idea here. But what I am seeing is this in this case right here. What I do see, did you stop highlighting that? Okay. What I do see here is if we were to do the multiplication here, we would get one copy of e to the x squared, which we know we can't do. and we would get two copies of x squared e to the x squared, which I'm skeptical about us being able to do. So I am double skeptical about this one because it seems like this just has two parts that are a thing I know I can't do and a thing I don't think I can do. So I am skeptical about this one right here. So this one's going to get at least a frowny face right there rather than a question mark because I don't think it's going to happen. But let's take a look and see what happens if we just kind of try some of these. What do we think is integrable? What isn't? So let's take a look at a couple of these guys here. And again, I'm just going to do what I've been doing in the last couple of videos, which is what you should be doing, which is just try it. Just try some stuff. Try the things that you can think. We that's kind of the whole point here is struggle through this a little bit. So let's just try some stuff here. If I pick a u, I think that x squared is a pretty smart u. Du is going to be 2x dx. If that's the case, then I am a little bit stuck right here. I can do this as e to the u, but like what's dx going to be? Uh, I guess it's going to be, I could even actually sort of like solve for it here. It's going to be like du over 2x equals dx, whatever that even really means to me here. Du over 2x. So I guess this will be like e to the u over 2x du, and I guess x is the square root of u. So have I like helped myself here? E to the u over root u du. Can I parts this now? This should be the integral of like u to the negative 1/2 e to the u du. What I know about parts here is that this guy is never going to get down to being a power of 0 because it's kind of offset from our integer powers here. Derivatives and integrals of fractional powers are always going to remain as fractional powers. So I guess I don't know. I guess I could try some u sub with this thing right here, or maybe some m sub, right? Because we're already using u. But I'm stretching for some stuff right now, but I want to emphasize that stretching for stuff is okay. I'm gonna make an awfully hearty stretch at the end of this video here today. Um, that's gonna be tough. So like, I don't know, did I help myself here? I know that get a little bit hard to read right there. All I've done is built this up to be now an integral with a one larger power than this one right here. So that doesn't seem to be helping me. I don't think that this guy is going to be anything that we're going to be able to actually handle right here. I really wish that I had this part of like this x that was in there. And that's exactly what we see coming up in this guy right here. With this one, this is our much more direct u sub right here, picking u to be x squared. Du equals 2x dx. I've clearly got my 1/2 du here for x dx, and it looks like we can very easily rewrite this guy as the integral of so x dx, that's 1/2 du, so that's 1/2 du, and e to the x squared is now e to the u. And there we go. We've got ourselves a nice easy antiderivative for that guy right there. We can take the derivative, verify that that will exactly get us back to where we were. So this is the one easy one on the list right here. So we've got that guy. X squared. Let's see if we can monkey around with this guy a little bit here. Again, if I try to make some sort of like u substitution here, u equals, I would be inclined to do something like this again. I can't really imagine what other substitution I'd make here. 2x dx, again, I could do this like kind of dumb maneuver here. I don't even know if this is actually like helpful right here, but it looks like I could rewrite this as like the integral of u e to the u and then du over 2x, and again where x is square root of u. So this is going to leave me with the integral of root u e to the u du, 1/2 of that. And again, this fractional power business right there is going to make this awful hard for me to, again, we're in the exact same boat as we were in for the parts in before. When we tried to do parts up here, the only difference between these two problems now is that instead of being a negative, it's a positive, but it's still got the exact same issues where we're just transitioning into other powers rather than kind of eliminating a polynomial term right there. So we're going to run into the exact same issues with this one where we can't quite get at this guy right here. Again, if you're being very hopeful and trying hard, then integration by parts would be a good thing to attempt right there, but it doesn't seem like that's going to be happening for us right there. Probably, but maybe it's something that's worth trying here. Maybe some parts in is what we're trying to do right here. So maybe instead we do something like u equals x squared. In that case, dv would have to be e to the x squared dx. But I'm immediately realizing that that doesn't work because I would have to be able to integrate this, which I know that I can't do. On the other hand, it seems like we could make a different choice here, so that didn't work. It seems like maybe we could pick like u equals e to the x squared maybe, and then du is 2x e to the x squared dx. In this case, v would be x squared, and or dv would be x squared dx, and that would leave us with v being 1/3 x cubed. I guess this is a thing that I could write out then, so then my integral would become uv 1/3 x cubed e to the x squared minus integral of v du. V du, I'm going to get overall my constant coefficients out front. I've got a 1/3 and a 2. It looks like I've now got a x to the 4th because there's an x here and 3 of them there. E to the x squared. So I technically wrote out some part stuff, but all I ended up really doing was doubling down on the power that I have right here. My hope with integration by parts is always that we're going to experience like that decay of those powers that are sitting out there, and I did not end up seeing that happen right there. So that one didn't work out. So what else we got to try here? I don't have any trig stuff in here that I can work with. I don't have any radicals for substitutions. This just seems like something that's not going to work out for us overall here. So this one gets its third X mark right here. This final one right here, again, you should be incredibly skeptical about this guy. We weren't able to do e to the x squared. We weren't able to do x squared, e to the x squared. But the whole purpose of us looking at this right here is to remind ourselves that we should maybe just not be as intensely skeptical as we otherwise feel inclined to be here. And so I'm going to make a slightly different substitution on this guy and see if we can finagle something to happen here. So what I'm recognizing here is that this is really just the same thing as the integral of e to the x squared dx plus the integral, and I'll just say it 2 times x squared e to the x squared. Yeah, so that's basically what I'm going to try for this one right here. Yeah. No, you're good right there, Coffee Gopher. And again, we want to like try all the substitutions that we can try out here, right? In this case right here. So, and in fact, look, let's just do that one right here. Another one that we're thinking about right here. And again, we're looking at the integral of x squared e to the x squared dx. And so what I think the motivation here is, why should we even see this one? What Coffee Gopher's seeing here is that the whole point of this e to the x squared thing is we really want an x coefficient with it. So I'm going to think of it like this. And now maybe do something like u equals x, and then dv equals x e to the x squared. Now this is something that we can integrate. We actually just did this problem right here, and we got 1/2 e to the x squared. I can say du is dx. Right? And in this case now, it looks like I am saying those parts went together, right? And then that part went together as our u there. So I've now got my uv, which is 1/2 x e to the x squared minus integral of v du. And in this case, our v is e to the x squared, and it's dx. Okay, so this is by far our best route. So Coffee Gopher, good for you. This is definitely our closest one. But the problem is, we still can never do this. We're now just back to the same integral problem of the integral of e to the x squared that we can't actually handle right there. So again, this looks like something that, this is clearly like the best case right there. We did a bad u sub that didn't work. I tried integration by parts that really wasn't going to work. I tried my next smartest, I thought, integration by parts, but it still wasn't what we were looking for. I then stopped and thought to myself, well, really the e to the x squared needs this partner of an x here, so maybe we rip apart x squared into 2 terms, and that actually got us a pretty sensible integration by parts statement. Like this one at least went in like the wrong direction. This is a simpler integral objectively right here. It's still not a doable one, but it's a simpler one right there. So, but still, I can't do that. So it looks like we're still stuck right here, right? So this seems like a good idea though. And the thing I'm noticing here is that maybe this is going to be a good idea over here. So we're still stuck with this guy, but if we do our same parts going on with this one, this is going to be the same idea here. X times e to the x squared dx. And I'm going to make my sort of same choices here. U equals x, therefore du is dx. Our other components are dv is x e to the x squared. This is the one that we already did up there as our example. This gave us 1/2 e to the x squared. And all I'm trying to do is just parts out this guy. I know that I know nothing about this integral over here. So it seems like what we're going to be left with is we got a uv. Oops. Oh, don't do it. Okay, thank you. 1/2 uv is x e to the x squared, and I got the 1/2 from v right there, minus the integral of v du. And hopefully you can see the magic that is about to happen right here. We are stuck with this integral of e to the x squared that we cannot do. But it turns out that they just canceled. Look at that, a positive one and a negative one. It looks like our answer here is just x e to the x squared plus c. I am assuming it is a surprise to you that this was the doable one out of all of these here. Okay, there was one other one that was doable. But that's a really weird thing here, right? So just because we have parts that separately aren't manageable, it doesn't mean that all the unmanageability won't actually just cancel away in some of these cases right here. I love these like kind of these sneaky roundabout ways that some of these things actually come together. I know that I've talked to you guys a bit about some of the things I was working on this summer were some very, very related ideas. Some of the math I was doing this summer had to deal with computing sums. Um, and the maneuver is to say, well, you're desiring to compute the sum of some function, f sub I of x, where I goes from 0 to n. And so, but the point is that this is completely unknown. And so the move is then is that you come up with two different sums that represent the n plus 1 version, and you set them equal to each other. And what happens is a bunch of their parts are going to include, it's going to be in terms of this, and then you're going to get a bunch of parts that are going to cancel away so you can solve for what the remaining pieces must be. This is sort of like our dump truck integration, where at no point did you actually do the integral. You just found several alternate expressions for the integral, combined like terms, and said, well, that must be what it is right there. And so there's some really interesting integration sometimes that happens this way. So the lesson that you're supposed to take away from this example right here is you really need to just try some things. Don't look at something and be like, I'm pretty sure that's not integrable. Because you will be made a fool of in most cases. Trust that integration is always something that we need to make efforts at to make it happen here, and that you need to make efforts without knowing that that effort is going to be fruitful for you. It's going to be the case that you're going to go down lots of wrong roads. In this guy right here, I tried 3 wrong things before I tried the 4th thing. That's honestly the best possible answer I could have come up with, but it's still wrong. But still, like that is at least the smartest way to go about this right here. But again, there's nothing wrong with this. This is how people do integration here. Is it definitely takes some effort on this. So I really like this problem right here. It's 2 impossible integrals together actually become possible, and it's good to kind of see that that stuff can happen. So let's talk about what this section in a sense is actually about here. What are our strategies for integration? And then I'm going to come back and do some tough ones from this section here. I like that in this section they don't actually do any of the integrals. They're just like, you can do these integrals here once you rewrite them in this way. I want to actually do some of these because I want to show you that just because you think you got stuck, you probably aren't actually stuck, and you just need to try harder. And I hate that this is not formulaic as so much other stuff that we've learned in the past. but I just do love the fact that like the people that can do epic integrals are the people that try the hardest, like in most cases. I like that integration is very often an effort-based success type thing here. If you give up early, then you're the one that gave up early. Don't do that. So strategies for integration. This is the same stuff I've been shouting at you for the last couple of weeks right here. Every integral that I've seen with you, I have said the same things to you. Well, I don't know. Can I just directly do it? That's always my first hope. Step 0. Does this take no special technique? Step 2, always do as much algebra as you can before you do calculus. That's a thing I've said to you many, many times. You're either doing algebraic manipulations, or if we have a bunch of trig functions, then you're maybe doing some trig substitutions. If you see sine x times cosine x, then hopefully we can look up the fact that that's going to be 1/2 of sine of 2x, and now we can move on with our integration. Number 2, and by the way, I hope that you believe that I have rephrased these slightly relative to how the book phrased them. Hope for U substitution. U subs are almost always our easiest friend, although I'm going to show you the worst case U substitution that could ever happen to you. That's almost guaranteed to be a lie, what I just said right there, but I'm going to show you the hardest U sub I've ever done in my life, probably at the end of the lecture here today, to show you U sub is usually really nice. It very typically simplifies our expressions into something simpler. When I think of U sub, what I picture is this example in the middle right here. Something vaguely complicated down to something that is like a trivially easy integral right here. U sub does that for us kind of a lot. It turns complicated things into trivially easy things right there, but not always. I'm going to show you the gnarliest U sub you've ever seen later here. In general, for our U sub, we're always looking to identify one component of the integrand whose derivative is also in the integrand. In the case above, we saw that we identified x squared, and the derivative of x squared, 2x, was also in the integrand, give or take a constant multiple. The other thing that we occasionally do with these U subs is identify one component of the integrand that is a linear transformation of the other component, where we've done a couple of these where we do something like u equals x plus 1, but then it's actually helpful for us to do like u minus 1 equals x and get some other, flip around some expressions in there. So those are occasionally things that we do as well there with the U sub. Not necessarily a part and its derivative, but some way to maybe say, like, if you have a sum in the denominator, you can maybe get that rewritten as a sum in the numerator instead, and then you can rip apart a fraction and integrate, stuff like that. Step 3, we always hope that we can just do the easy stuff up here first. Step 3 is really the meat of this stuff that's right here, in my opinion. These are a bunch of our more difficult techniques out here. Powers of trig functions. We saw in section 7.2 that if we have things like sine cubed times cosine to the 6th, powers of products or ratios of trig functions, then there are some suggested substitutions that we can make. All of those are emphasizing the fact that the Pythagorean identities, things like sine squared plus cosine squared equals 1, are going to be good substitutions to help us move around our parts, to help get down to just having one trig term that we can eventually integrate. Whenever we see rational functions, we are probably hoping that we don't quite have to do partial fraction decomposition, because it usually takes it takes a lot of easy effort. When people get upset about partial fraction decomposition, I always like to think it's like, out of all the complicated trig techniques, the easiest one for me to do very tired is partial fraction decomposition, because it's just algebra. It's not really calculus. As I did not do an example yesterday, but I made sure to assign a My Open Math homework with a video, is that sometimes we need to do a little bit of polynomial long division before we hit our partial fraction decomposition. But again, that's stuff that you learn in algebra class. It's not a calculus technique, it's an algebra technique. Integration by parts. If you ever identify that we have a product, right? The integration by parts is sort of like our product rule, except it's more of a guideline than a rule. If we have a product of a polynomial and a trig or exponential or log function, it's good for us to give an attempt at integration by parts. What I think the hardest thing about integration by parts is that it's harder to pick your parts. Similar to U sub, you've got even more parts to pick. You saw right here, I made 3 separate attempts at integration by parts for a not very complicated problem right here. I made 3 separate attempts. None of them worked. One was clearly better than the others, but not great still. And so integration by parts, you've always got choices. And so, keep trying. Don't just give up if you've tried one part and it didn't work. There's always multiple ways to go about it. Anytime you see a radical in an integral, you are kind of hoping that you can either get rid of it or use some trig functions to get rid of it. If the stuff that's underneath the quadratic or the radical seems quadratic, then it seems like you should be able to use a trig sub to get that thing out of there. Otherwise, u subbing the entire radical expression, that was an example that I did last class, is a good move there, and we'll in fact see another one of those today. Number 4, I certainly rephrased from the book, the best advice you can ever be given. From now on, math is going to be hard forever. There's not going to be easy math that you will ever do again if you are in this class. There is going to be 1,000 problems that you're going to hit once with no reasonable success whatsoever, and you need to learn to just try a different route. Think of a different way that you can attempt the problem and then give it another shot. If you feel discouraged after one thing doesn't work out, you are going to have a hard time with the rest of your math career. Like, you're going to make lots of mistakes. That happens to literally everybody. Don't get discouraged by that. Every single non-basic integral, non-direct integral that we've done has boiled down to either performing a substitution, performing integration by parts, or performing some version of algebraic or trigonometric manipulation before we hit the integral. To me, integration is as much of a psychological battle as it is an academic one. It's rarely the case that you've never seen the technique needed for the integral. It is often the case that you get discouraged and you're like, well, I tried everything, when you really didn't. And so seeing what all of your choices are and recognizing that you might have 9 different ways to attack an integral before you do it once is a good thing to do, because it's giving you a way to say to yourself, there's always something else I can try out there. And saying those things to yourself, and you know, I know that people generally hate hearing this, but it's like, be positive, right? Like, you do want to talk yourself into the fact that you can do this stuff. And if you try and be like, well, that didn't work, I'm screwed now, then you are the one that's not going to be able to figure it out. And so don't do that to yourself. Like, you have to kind of stay positive and focused on a lot of these things and say, I'm going to be able to work my way through this for sure. And the other comment that goes with this, I guess these are sort of my bulleted hyphens, is remember to reuse old results. Sometimes people get stuck being like, well, that just got me to another place I can't go. Remember to reuse old results. The book gives this little brief example right here of just saying that, you know, don't forget that we can. Pardon, Reed, is that am I losing things here? I think that I see that my internet seems nicer to me today than it was last video here. Might just want to try to refresh. Um, Hello. And so remembering that we can make a bunch of these substitutions here. I'm like forgetting my basic substitution right here. What's my that in this case, for example, tangent squared is secant squared of x minus 1 times our secant of x dx. And if we multiply this guy out, this is secant cubed of x minus secant of x. And it turns out that we have individually done both of these integrals in previous sections out there. So sometimes your rewriting is going to lead you to things where you're like, well, I don't know the integral of secant or of secant cubed. But we've done both these. They were both hard. They both took a bunch of work. Reuse those old things. You know, this might be a thing where if I were to give this problem to you on a test, maybe you say, and we worked out in 8.2 that secant cubed was this, and in the book they work out that the integral of secant is this, and therefore the answer is this, right? Nobody's looking for you to just write up pages of stuff that you've already written up before. So recognize when you see something that you know you've done before, and you know, you need to be competent and capable. If you're going to claim that you're referencing an old result, you can't just say, and we know that this response is this. But if you've got the good justification that we've done it, then claim your old results right there, right? So sometimes just remembering that something is something that we've seen before is a meaningful thing to do. So I just want to work through a couple examples here, and in particular, the ones that I want to work through are the ones that the book, so the book does a good job of not actually doing any integration, but just manipulating integrals until they have convinced you that we're good to go. And so I would now like to actually do these problems in their entirety and see that we get in many, many cases, alternate routes here. The reason that I want to do the problems that I'm going to do today is because I want to show you that there are very often alternate routes. You might have come up with a completely different technique for a problem than somebody else did, and it's perfect to do that. It's good to look over and see that maybe somebody's was more effort or less effort, but maybe your more effort way is something that's going to apply more generally to a broad variety of cases, whereas maybe the route that your classmate did that was easier is a much more specific to the instance at hand. And so comparing and contrasting these things is how you get the intuition to be good at this. And so it matters that we see these things go lots of different ways. So the ones that I want to look at right here are these two guys. They're both, this top one's going to not be too bad. This one's going to kick my ass down here. I am actually still a bare smidge stuck on one of the routes for this one right here, and I will show you exactly how close I am, and maybe I'll have a moment of inspiration. But I'll actually tell you, we're looking to do sort of 4 different problems between these two right here, and one of the 4 I'm off by a hair, and I want to find out where it's going to be here. So let's take a look at these guys. And again, I'm going to do both of these 2 different ways. And that is, in my mind, the highlight of this whole unit is doing things multiple ways to show you, like, don't feel like there's some algebra or some recipe for doing these things. And if you didn't see it, then you're screwed. Lots of these things have lots of different ways to go about them. And you should be okay with kind of hunting out those options for yourself out there. So what do we want to do here? So I'm going to do this one, as promised, 2 different ways. Um, when I'm looking at this integral here, again, I'm gonna allow all of my opinions to flow out onto paper right here. I don't want to discard anything. My first thing that I always think is when I see tangents with cosines, I always am like, who the hell wrote it that way? If we've got cosines in our problem, then why wouldn't we just write this all in terms of sines and cosines, right? Tangents, I don't know. What trig class taught me is rewrite tangent in terms of sine and cosine. So I'm going to say here for my route 1, and because again, I'm doing this 2 different ways. So I'm going to start the first version of my solution here. I'm going to think of tangent as sine over cosine. So I'm going to think of this as sine cubed x over cosine cubed x. And this is times. I still have my 1 over cosine cubed x from the original part right there, dx. And so it looks like I can maybe write this as sine cubed x over cosine to the 6th x dx. Now that we're here, the good news for me is that, and again, I'm kind of like I'm gonna do this a couple of times, and I'm sure it's gonna be slightly annoying to watch, but I want to really emphasize the list that we're looking at right here. I have already done some efforts to make some, for example, I've already basically done step 1. I just did some trigonometric substitutions there. As I said many, many, many times in yesterday's video, I don't know if it's helped me yet, but I did some. I'm going to hope for you substitution. I want to identify one component of the integrand whose derivative is also in the integrand, and we go down to ask ourselves, do we have one component where the other component is also in there? And we say, yeah, sine and cosine are in fact essentially derivatives of each other, give or take a plus or minus. And I'm going to go ahead and do the wrong one here just so that we can remember. I'm going to immediately say to myself, oh yeah, if I pick sine, then du can be cos x dx. And then I say to myself, oops, did that one backwards right there, because what I can see is that the dx is a numerator term, but the cosine stuff is denominator terms, and I need them to be equivalent right there. So that wasn't the sub I was looking for, but maybe if we instead do u being cos x, then du being negative sine x dx, maybe now this is a route that we can actually go for this guy here. So here's kind of what I'm seeing now. It looks like I know that sine x dx is a piece that I want here, and I know I'm going to pick up a negative in here. Okay, I'm not even going to write that negative in here yet. I know that I just want a single sine to go with dx, so I'm now going to rewrite this as sine squared x sine x dx, all divided by cosine to the 6th x. Well, cosine is just u, so it looks like we've got a u to the 6th on bottom. So this is sort of like I'm doing my mixed u subbing here, right? And I think that's okay. So now what I'm thinking to myself is, well, I know that sine x dx is just going to be du. So the only part I have a problem with is sine squared of x. And the only way I have to convert it into u stuff is with a cosine. And so the good news is we've got a Pythagorean identity that can help us out with that guy. 1 minus cosine squared of x. This is now just our du all over u to the 6th. And it looks like now I can rewrite this guy in terms of u. So I'm seeing here integral of 1 minus u squared over u to the sixth du. Feel pretty good about that guy right there. It seems like this is nice and simplified right here. So this is the integral of 1 over u to the sixth minus u squared over u to the sixth du. And one more algebraic simplification before I integrate. U to the negative sixth minus u to the negative 4. This is not, we're basically done right here. This is where the book stops. I just want to get down to a final answer because I want to be able to compare my two techniques and see that I got to the same answer, and I'm not going to make the same type of substitutions. So I'm not going to get two expressions that are similar in terms of u. So now I think I should be getting here. We're going to add 1 to the power because we're integrating. So the power is going to become negative 5. But if I were to take the derivative, it would pop down a negative 1/5, or it would pop down a negative 5. So I need to cancel that with a negative 1/5. Oh, and by the way, now that I'm seeing my negative right here, I'm realizing that when I made this substitution, that introduced a negative right there. Du was negative of that stuff. Right? I forgot my negative right there. That negative right there, I forgot. It goes right there. Boom, boom, boom. Right? Okay, so I've still got all my stuff right here. Maybe now I can just go ahead and do this. Negative. My other one here, minus u to the negative fourth. We're going to add 1, so we're going to get a u to the negative 3. But if I were to take the derivative, it would bring down negative 3. So I'm going to keep negative 1/3 of that. And get my plus c. And so it seems like got a whole bunch of negatives out here. Yeah, okay. I see that these two are going to become, yeah, positive right there. So I'm going to get a 1/5 u to the negative 5th. This is, those two negatives make a positive, but then I'm distributing this negative in, so I do get a negative for this one, minus 1/3 u to the negative 3 plus c. And all I got to do is just restate this in terms of x, and we're good. U was cosine of x. So I think I can now write this as 1 over 5 cosine to the 5th of x minus 1/3, 1 over 3 cosine cubed of x, all plus c. Oh, what was that? Don't scroll me. Plus c right there. Okay. So there we go. So we got one of our versions of this guy right here. Yeah, I do have those in the right order right there, right? So good. So again, when I made my first alteration right here, I was not sure that I was doing the right thing. When I wrote tangent in terms of sine and cosine, it was a sense of shot in the dark right there. But I did that partly because I saw that I had some cosine stuff. And so I thought, well, the cosines from tangent might want to join up from that. That led me to a u sub. I made a wrong u sub at first. I do this one wrong all the time. I've done this a million times in my life, which is why I'm doing it wrong on purpose in my lectures here. I know that you guys probably are too. And the point is, who cares? Who cares if you set up a u sub wrong your first time? Do it again. You've always got, you can do these things, infinite attempts out here, right? Once I set up the correct u sub, things kind of fell into place. Remember that you can always rip apart powers of things. Grab the pieces you need. If you're saying to yourself, well, in this case, I would need a sine x dx, get one. Like, make that be part of what your expression looks like. Sine x dx was there. We just had to kind of separate some of our parts. And then, even powers of sine can be rewritten as powers of cosine. And then that kind of took us the rest of the way home. Like I said, the book got to here and stopped. Right? That was the book's kind of stopping point. And they said, and you can now finish this problem. Or maybe they got to like here and stopped, whatever. Once we're to here, we're doing our simple integration right here. So that was route 1 on this one. This is one thing that we could have done. Let's go ahead and take a look at an alternate solution for this guy. Now, the other thing that you could have said to yourself is, well, I think it's weird to divide by cosine. We have a word for that. Why would you divide by cosine if we can think of that in terms of the trig function that we actually call it? And so here, an alternate way of rewriting this into something more palatable for ourselves is tangent cubed times secant cubed of x. And it turns out that this is exactly the type of situation that we looked at in 7.2. We saw that when we have products of powers of trig functions, then there are recommended substitutions that we would want to make. In the case that we see, our book told us in 7.2, If we have odd power of tangent, then we want to isolate a tan x secant x term and use the sub u equals secant of x. Right? This is just the recommendation in the box from section 7.2. They just said, hey, listen, if you see odd powers of tangent with any powers of secant, then isolate one tangent secant grouping and then do this recommended u sub right here. And again, I really want to emphasize how I expect you guys to think about this. I think it's reasonable for you to either guess this manipulation of the integrand or to guess this manipulation of the integrand. I think it's perfectly reasonable that everybody in this class should be able to think to rearrange it in one of these two ways. If you get to this route right here, I absolutely expect you to think of u sub because you see parts and their derivatives in here. And once you get the u sub, you're cruising. If you get to here, I expect you to remember that we covered section 7.2, and I expect you to just go look up this rule. This is one where I knew when I saw it, I was like, oh, I'm definitely gonna, I know the stuff I'm doing right here. I know what I'm doing. And I actually did it wrong twice. If you look at my notes, I just have a bunch of crossed out stuff right here, and I had to go back because I kept on wanting to use a substitution with tangent instead of with secant. If we have even powers of tangent, that's when we want to do u equals tan x. And I forget that little technicality. I don't care if you forget it. I care if you choose to go look it up or not, because the book clearly explains to us if you have odd powers of tangent with tangent stuff and secant stuff, it literally says like this phrase in 7.2. And you should be able to go find that and be like, oh yeah, that's what we do, and be able to do it, right? So let's go ahead and actually do this technique now. So we've got the integral of tangent cubed x and secant cubed x dx. According to the advice that we got from 7.2, I want to instead think of this as tan squared x secant squared x times tan x times secant x times dx. The book's advice said isolate one tangent x secant x expression, so I just ripped it out of the parts that we already had. Then use the u sub u equals secant of x. And again, I am in a sense right now kind of blindly following the book's advice, but I have learned to trust the book's advice in 7.2, so I think this is a good move on our part. If we make u be secant x, then we know that the derivative of secant is secant tangent, which is why they're recommending that we make that that isolation right there. So there we go. We've got our du. There we go. This is going to be u squared. And it looks like tangent squared we're going to want to rewrite in terms of secant squared, and we're going to be able to do that with our Pythagorean identity here. So our Pythagorean identity here is going to be that tangent squared of x equals secant squared minus 1. So let's go ahead and use these three pieces of information to get this guy done here. So I'm now going to land at tangent squared is secant squared x minus 1. Secant squared is just u squared. Tangent times secant times dx is all just du. And we're in really good shape now. It looks like this is going to be u squared minus 1 times u squared du. And this is even easier than the last one. Wrap this guy up here. 1/5 u to the 5th minus 1/3 u to the 3rd plus c. And all we got to ask ourselves was, wait, what was u again? U was secant here. And we know that secant is 1 over cosine. And so we got the exact same answer as we got in the previous route right here. And again, I really have a hard time thinking, oh, that should be a secant cubed. A really hard time saying that one of these methods is better than the other. It's more important that you are able to see one of them, right? The reason I'm doing this two different ways is to give you, as I said earlier, integration is a psychological battle. What I'm trying to do right now is give you the psychological fortitude to know that just because the substitution that you maybe made first isn't the same as what somebody else did, neither of you are necessarily wrong. There's lots and lots of ways to go about lots and lots of these problems here. And I want you to kind of always go into every attempt saying, maybe this is going to work out for me. Maybe this is the thing that's going to take me to the right place right here. And again, these are things that I hated being told as a student, but that I now know are true. It literally helps to have a positive attitude when you're trying these things because like it's not obvious that the moves you're making are helpful until you've followed them out for a couple steps of the way. So you have to just keep going until you know. Yeah, more than one way to skin an integral. It's man, what a weird phrase that ever even is right there. Much better with integration than with cats there. So stay positive. Try some stuff. Be confident that you are a competent person that is capable of making things happen and just follow your work. You are really going to see that lesson bear out in this example right here. This guy has a smart thing to do and has a gnarly beast thing to do. And I think this is a super cool problem right here. So this problem kind of sucks. I have a much harder time saying that I expect you to know a manipulation or a substitution to do with this guy right off the bat. And let me go back up to our previous problem and show why. In this guy right here, I think it's pretty obvious that there are some easy trig alternate representations to think of. Every one of us has rewritten tangent as sine over cosine over 100 times in our life. I expect that to be a vaguely natural thing for you to do. I think this is a easily completely fine problem for me to put on our test for next week because I definitely expect everybody could think of one of the two routes that I just thought of right there. And honestly, I think these two routes were like equally as difficult as each other. For this route right here, dealing with tangents and gosh, I can't say my words. Dealing with tangents and secants is always less comfortable for me than sines and cosines, so I did need a little bit of book help on reminding me exactly how to go about the substitution here. But who cares? I don't care if you go and look this up in the book. That's the reason that you own the book. It's not a secret. I really expect that you could see a possible manipulation of this one because we've all taken trig. This one's less obvious. I do not think that there is anything that should be slapping you in the face right here as far as some obvious thing that you should be thinking about with this one here. This one takes a little bit of like, what the heck am I even going to do with this one right here? So I do want to kind of cruise up the list, back up to the list here and talk our way through this one here. So our mystery thing right now that we're looking at is, in what order does it go in? Is it minus or plus on top? Minus on top. 1 minus x over 1 plus x dx, right? So that's what we're hunting around for. Talking myself through my list. Algebraic manipulation. Not obvious to me what algebraic manipulation I can do here. But I don't know. Maybe I could do something. Trig substitutions. We don't have any trig stuff right now, so that doesn't seem like it's it. U sub. Can I identify one component whose derivative is also the integrand? No. There's no one part of this where the derivative is also in here. Alternatively, identify one component of the integrand that is a linear transformation of another component. This is actually pretty close to something that's happening in here, but recognize that our issue is still just going to be if we have a couple different gross terms both stuck underneath that square root, we're kind of screwed. I really feel like the external square root here is our bigger issue than the difference between the plus and the minus in the fraction that's going on right here. But again, that's sort of just like intuition that's telling me that that's the problem. I don't know. Classify it according to its form. Powers of trig functions, don't have it. Rational functions. Our problem isn't that it's a rational. Our problem is that it's the square root of a rational. Integration by parts. I definitely don't have like a product of some parts in here that I can rip apart. Radicals. I do have a radical. If there's a quadratic under the rational, use a trig sub. That's not what we have. Otherwise, try and u sub the whole radical expression. Well, that technically sounds like our situation. I don't really want to do that, but that recognize that technically agrees with our current situation right here. So, and the try again, of course we're going to try again because we're going to do a bunch of crazy things to coming up to try to do this guy right here. Reuse old results, sure, I'm going to do that. We are actually going to see one old results right here. It's from an example that the book does that we actually didn't do, but I'm just going to claim it and use it because this one's going to be gnarly enough right here. So here's my disappointing thing. Out of my list right here, 4 is never like the strategy that you use. 4 is just your reminder to never give up. So what I'm seeing here is it seems to me like I haven't really tried any algebraic manipulation yet, so we should try that. And it does unfortunately seem like this is representative perhaps of our situation right there. So that might be something I want to try too. So I'm thinking our two routes to this guy are let's try to algebraically manipulate this and let's see if we can just use up literally the whole expression right here. Pretty skeptical about this one, but we're going to try it. So let's come back to where we're actually working here and try each of these things. So our technique one, our attempt one, is going to be algebraic manipulation. But what algebra am I even doing? Well, I don't know. At least one thing that I'm seeing here is that I know that like the square root of x over y is root x over root y. So at least kind of rewriting it like this as the square root of 1 minus x over the square root of 1 plus x. What this is sort of suggesting to me, and by the way, I'm literally going to go add this to my list right now. Oh, I don't want to hit enter that late. Um, I'm going to make that statement. Don't forget conjugates. Remember that conjugates, multiplying by a conjugate is a good way to make something look different. And one of the nice things that conjugates do is they end up giving us a squared representation of something. Nice pyramid there, K-Ways. Seven's pyramid. I've never seen that before. So some algebraic manipulation I might think to myself is it'd be pretty cool if we could like rationalize a denominator here and see if we can get some other parts or something like that. And again, I don't really know what it is that I'm doing right here. I'm trying some stuff, right? So I'm going to hit this thing. I know that I don't like having radicals in my denominator down here. So I'm thinking that maybe we can do a 1 minus x and excuse me, wait a minute. See, I'm already losing track of the thing that I was looking at right here. And again, the point is try it both ways, right? So this is equal to 1 right there. There's my conjugate. And so what I'm thinking to myself here is it's maybe going to be nice if we rationalize one of these parts or the other. And so I'm kind of thinking to myself, I wish I would have set this up two different ways right here. Here's the way that I kind of want to write this now. Let me do this. The other thing I could have written this as is square root of 1 minus x over square root of 1 plus x. And maybe instead, I would have hit it with the other conjugate, right? I'm literally trying all my stuff right here. I'm not doing guided work. I'm making attempts at things. If I were to do it this way up here, then what it looks like I'm going to end up with is the integral of square root of 1 minus x squared over 1 plus x dx. And that looks like, I don't know, maybe something we can kind of work with. Alternatively, if I do this guy over here, I'm getting the same term as on top, so I'm just getting a 1 minus x. And in the denominator, I'm getting a 1 minus x squared. Now, what we want to ask ourselves is which one of these two is a better way to go? I'll call this option A. I'll call this option B. I'm kind of thinking to myself that I kind of like the look of this guy because this I can now rip apart into two different fractions, right? Because we've broken ourselves out of the radical in the numerator. The reason why I like this option slightly less is because this denominator, we can't rip apart denominators, right? 1 and plus x, we can't split that, whereas we can split numerators, 1 minus x, into two fractions. We also can't split this numerator here into two different pieces because it's underneath the square root. So this doesn't allow me to deal with any of these components separately based on this option A right here. So I am going to kind of go with option B in this case right here. And I think then that I can rewrite this as the integral of 1 over the square root of 1 minus x squared dx minus the integral of x over the square root of 1 minus x squared dx. And the nice thing is that evaluating each of these integrals, we've done both of these before, which is good. And what's good is that we know that the guidelines associated with these square roots, and in fact, here's what I'm going to do. I'm going to keep on referencing this list here. I'm going to scroll back up real briefly here. Back in our list, it says Oh, if you have radicals, if a quadratic is under the rational, do a trig sub. So this is how I know to go back to look in section 7.3. If you look in section 7.3, it's going to tell you, listen, if you've got a square root of a minus ax squared, then you're going to be wanting to do x equals a sine u right here. I'm thinking to myself, 1 minus like sine squared is cosine squared, stuff like that. So I'm thinking to myself, I want x to be sine squared. Sine squared of what? Of our new variable that we're introducing to handle this. Oops, I just did that slightly wrong. Okay, all right, that wasn't too bad right there. Um, a minus ax squared, then we want to choose x to be a sine u. Oh, I think they don't put the parenthesis right there because then you get the a squared right there. Anyway, the point here is we're in the same radical situation in both of our integrals, right? So we're going to pick that same substitution here. Remember that the tricky thing about our trig subs is that they kind of go backwards. In u sub, you say u equals something, but when we do our trig subs, we sub backwards. We say that x is equal to something in terms of u instead. And so actually for both of these, I'm going to do the same thing, but I'll deal with each of these separate here. I'm going to do x equals sine of u, and therefore dx equals cos u du. This is going to allow me to rewrite this integral here as 1 over square root of 1 minus sine squared u. Dx is cos u du minus the integral of, I'm using the exact same sub for both of these because they're both the same radical term right there. It looks like this one's going to give me a sine of u over the same stuff. 1 minus sine squared u cos u du. And so let's see if we can wrap up these two integrals right here. Looks like this guy is going to be 1 over square root of cosine squared u times cos u du. Looks like this one is the same thing, just with the sign on top. And notice what's happening here. The square root of cosine squared is cosine. 1 divided by cosine times cosine. This is literally the integral of 1 du. That worked out about as nice as it literally ever could. Similarly, you should notice that this is the same thing, just with a sign in there, sine u du. This is divided by cosine, this is times cosine, they canceled right there. So that actually worked out excellent for us here, and we're actually done. We're just going to need to get back into u land here. The antiderivative of sine is negative cosine, so we're going to get a plus cosine u, right? Negative of a negative right there, plus c. And we just need to know what's u, and we're good here. Well, it looks like we have x equals sine u, so we're going to need to get ourselves some help here. So I'm going to bring this down here. U plus cos u plus c. And we did the substitution x equals sine u. So it looks like what I need to do is things like 1, u is sine inverse of x, and that's good because now I've got one of my parts of my answer. Plus cosine of sine inverse of x plus c. So all I've got to do is just get a better expression for this guy and we're done. I'm just doing a little bit of trig stuff right here. I like to generally say to myself, the things that we get out of, actually, never mind. I'm just going to write this as the triangle that it is right here. X over 1 is sine of u. So that would be my u right there. That's apparently the angle that we're taking in. Sine is opposite over hypotenuse. So therefore, our other leg here is 1 minus x squared. And now I can take the cosine of u. So really, I think I just wanted to leave this as like u right there to be most sensible. Cosine of u is adjacent over hypotenuse. And so this should then be, for our final answer here, sine inverse of x plus, it's just this term right here. Obviously, over 1 does not matter. I'm just writing it to make sure it looks like where we came from, the triangle right there. So this is a hard problem right here. And it required us to do an algebraic manipulation that I know is one that all of us think about slightly less often. So I want to kind of come back to that conjugate thing. So remind yourself that like square roots are generally not your friend, and so getting rid of them is your friend. Ripping apart square roots into several individual ones is typically a good move. We wrote that as a root over a root right there. And here I tried two different conjugates. I tried both the conjugate of the denominator and the conjugate of the numerator. This one allowed me no rip apartable pieces, right? I couldn't separate the numerator and I couldn't separate the denominator. Over here, this not only gave me a separable numerator, but it gave me a denominator that I actually recognized from all of our trig sub stuff over here. And so again, I don't want it to feel like I'm just stumbling around in the dark, but like you guys should kind of keep on realizing like it feels like you have a million options, but like no, you had two options. Which of the two conjugates did you want to try? Look at both of the results, decide which of those you want to actually work with for integration. These were both relatively easy integrals as far as 7.3 is concerned. And in fact, they even use the exact same substitution to handle them right there. Like, it's not going to get any nicer than that, doing two integrals that require the exact same u sub. Like, pretty nice right there, right? So the rest of this is us just doing 7.3 stuff over again right here. So now I would like to do the hard problem for the day right here. This is the, ooh, this is the one where I got a little stuck, but I really think it's worth seeing this right here. This is like a very important struggle that I experienced that I hope that you guys are doing things just like this here. So this is my route to this one. And what I know is that my answer here is technically off by a bare smidge. You're going to see how satisfyingly close that I am, and I don't quite know where it is, but I don't care that I'm right or not. I want you to see the thoughts that I have because some of the strategies that I used in this one are different than strategies we've seen elsewhere. So here we are. So I'm going to come back up to our list and remind us of what exactly our other alternate strategy was. Back in our list over here, we saw two things. We saw one, we should just do algebraic manipulation. And I added in the comment, don't forget conjugates, because conjugates are something that we kind of forget as far as an algebraic manipulation, because they often feel like they make things more complicated. But when you get squared terms, that's often good for us for trig and for trig sub. So conjugates, generally helpful. Don't forget about those. The other thing that we identified was that if we have a radical in our integral, the suggestion is u sub the whole dang thing. U sub the whole radical expression. When I say the whole radical expression, I literally mean including the radical itself. That's going to kind of suck for us here, but I want to show you how it really actually works. And again, I'm going to get the wrong answer, but you guys are going to be happy with this still. This is a sweet problem. This is like the happiest integration I've done this semester here for myself here. So what this is suggesting to us is that the u sub that it's claiming that we want to make is this one. And this, I hope, feels to you as useless as it looks. So here's where I'm at. Thing one, the last thing on earth that I want to do right now is try and do du. So that's all I'm going to write there. What I'm going to do is I'm going to do my lazy man u sub, and I'm going to say, well, so far what I have is u dx. What I really want is a dx expression. So what I'm going to do is I'm going to solve for x in terms of u. Then find dx. So what I'm going to do is I'm going to take, what I'm not going to do is just take my derivative of u right now. I think it's going to be too gross for me. Can't do it. So what I am going to do is I'm going to take this u expression here and I'm going to solve it for x. We're about to go on a hefty algebra adventure here. So I'm going to solve this guy for x. So I'm going to multiply out the 1 plus x. I'm going to get all my x parts together. So x is going to go to the left, u squared is going to go to the right. Factor out an x. And that's going to leave me with, oh, here, let me just do it this way. X times 1 plus u squared equals 1 minus u squared. And that's going to tell me that my alternate way to kind of flip this all around is that x should be 1 minus u squared over 1 plus u squared. All right. So now I have an expression for x that's maybe useful to me. Now that I have an expression for x, I can now use this to find dx. Okay, so now to find dx, I need to take the derivative of this and stick a du on it. Okay, looks like we got some quotient rule. Low d high minus high d low, all divided by low squared du. So this is apparently my good expression for what dx is. I mean, I'm right. Again, I'm going to say this for the billionth time. Is this useful to me? I have no idea yet, but we're going to keep going, try and find out here. Certainly, I want to simplify this before I go stick it back into my integral expression here. So what I'm seeing is I'm going to distribute this across that group. I'm going to distribute the 2u across this group here, and I'm going to get negative 2u minus 2u cubed minus 2u, making sure I distribute this negative as well. And so it looks like negative and negative is positive. So I'm going to get a positive 2u squared, or positive 2u cubed right there. All divided by 1 plus u squared squared. And the nice thing I'm seeing here at least is cancel, cancel. So it looks like we're actually getting that dx is negative 4u over 1 plus u squared squared. And I'm going to keep saying it. Does this help us? I don't know. But I'm going to keep trying stuff because I don't know what else I'd try here. If you didn't think to do the conjugate, I don't know where else you'd go on this problem. So notice that this right away is an interesting technique right here. I really didn't want to have to take the derivative of u because with the square root, now I've got a chain rule with a quotient rule inside of it, gross. And so instead, I solved the u sub for x, which took some work. I used the x expression to find dx in terms of du, simplified it a little bit. And I now think that based on these things, I can now come over here to kind of try and come back to my integral and work on some parts here. So it looks like we've at least rewritten this beast as u times negative 4u over 1 plus u squared squared du. That was my dx right there. And it looks like we can now rewrite this. I'm going to pull the negative 4 out front. U squared over 1 plus u squared squared du. Okay. Honestly, I think this looks better. I don't know what to do with this yet, but I mean, man, like what the heck are you going to do with this original expression right here? Like this is unreasonable. So I don't know what I'm going to do with this yet, but I feel like this is not an insane thing for me to do based on where I've arrived at by now. So now what I'm thinking is I now have a rational expression what I know is that partial fraction decomposition is a route that we can take to handle things that we need to maybe rip apart that are... Why is it doing... I clicked end. Come on, man. Did it move everything? Oh. Stay there. Seriously? Okay, I don't know where else to click. Okay, new page. We're allowed one more page. So here's where we're at. I need all the information in the boxes. I'm going to box all the stuff that I want to come back to use later. Unfortunately, we're going to have to use our subs to get back in terms of x later, get out of u, which is a little unfortunate, but we've at least gotten to a new place to be. So I'm going to try and deal with this, a little partial fraction decomposition. And so if I hit this thing with a little decomposition, then what I learned from our previous chunk here is notice that u squared on top is a little bit different right there. Our partial fraction decomposition here should say to us u squared over 1 plus u squared squared. Notice we do have a repeated factor down here. And so I'm going to break this apart as one copy, 1 plus u squared, as well as checking out if we keep both copies, 1 plus u squared squared. I'm going to multiply by the entire denominator here, and that's going to leave me with a u squared equals a times 1 plus u squared, because we only had one copy that canceled, so the other copy survived to multiply by a. This denominator here is identical to this denominator here, so we just get a b. Right away, I can see that it has to be the case that a is 1. And if a is 1, I can also see that a plus b is 0, and therefore b is negative 1, right? So I've done my partial fraction decomposition now, so it looks like we should be able to rewrite this integral. Really here I'm just thinking like that denominator doesn't seem horrendous, but with a u squared on top I don't know what to do. Now we have constant numerators up there, which is nicer for us. So now we've got a 1 over 1 plus u squared minus 1 over 1 plus u squared squared du. This is where I'm going to finally take a partial cheating step right here. The book has computed this integral right here previously, and I'm going to reuse the book's old results. This is one that you should recognize. This is the derivative that we got from inverse tangent. So the integral of this is inverse tangent. So it looks like what I'm getting here is negative 4 tan inverse of u, which is unfortunate because u isn't our final variable. Notice, oh no, I'm going to leave that negative out there. This is still a minus. This is the book's old result from this, is we're going to get a 1/2. Need to look at this guy right here. I'm going to put that 1. Don't do it. Okay, good. It's not doing my terrible. So 1/2 of, what do we get here? X over x squared plus 1 plus tan inverse of x. Plus c. All right, so, oh my gosh, hold on. I just did a bad thing. I wrote x's everywhere, and all those x's are u's. I want to rewrite this in terms of the correct variable here. This is u over u squared plus 1 plus tan inverse of u. Right? Am I writing this right? Yes. Okay. So we're kind of done. So here's the good news and the bad news. The good news is that we kind of did it, I guess, technically, maybe. The bad news is that we're still in terms of u, and we really need to be in terms of x. The good news is it looks like we have a couple different groupings of tan inverse of u. So I'm going to distribute this negative 4, simplify a little bit, and we'll compare our answers. Now remember that u was really the square root of the big gross thing, right? U is really the square root of 1 minus x over 1 plus x. Now we've got a plus 2 copies of u over u squared plus 1 plus 2, and again, 4 copies, but only half of that is another 2 copies of tan inverse. So I'm mixing my variables a little bit right here. Kind of what you can see is negative 4 tan inverses of it plus 2 tan inverses of it is going to leave us with negative 2 tan inverse of our gross expression plus 2 copies of right? There's u. That's u squared, so no square root plus 1. So I'm claiming that this is going to also be the same answer, right? Now before, so now we're asking, is this the same thing as sine inverse of x plus the square root of 1 minus x squared? That's what we got before, right? Same answer from the previous one. It seems wildly unlikely that these are the same thing right here. But our good way, if you ever get an answer that doesn't match and looks nothing the same, then what you know that your route should be is, let's go to Desmos and see what we see. So I'm going to now pop over into Desmos and I'm going to show you exactly what I see. And by the way, there's a really important part to this I keep not writing. right? Does plus these matter if we're going to compare answers here? These certainly don't look like they're going to be the same thing to me. So let's go ask Desmos what we see here. So I have typed each of these expressions into Desmos. Here's the result that we got. -2 tan inverse, the crappy square root expression, plus 2 times, and none of these parentheses actually need to be there, right? We're all within that square root term right there. That was all squared, right? So that's the plus 2u over u squared plus 1. That was the result that I got from the book previously. Here is the first answer that we got, sine inverse plus square root of 1 minus x squared. And what I'm seeing is I'm seeing these two curves that are clearly not exactly the same, but what we know about integration is that we're getting maybe different constants of integration associated with each of these. So my question is, well, maybe these are vertical shifts of each other. So I'm going to give a plus c to one of them and see if when I slide it, it lands on the other one. And I am like, I don't know. Is this, maybe I just need to get, much more fine breakdown here to where it's actually giving me some, oh, come on. It won't do step sizes that are that fine. So I feel like it's off by like a little bit, but maybe I'm just actually kind of want to like zoom in on this value down here and like see if I can get these two aligned and see if it actually aligns up top right here. I'm going to bring this down. Maybe that's like the C that I'm looking at right there. Also, oh my gosh, do you recognize what number I'm actually getting for C? Wait a minute. So these actually do match. I was just talking myself out of it earlier because I was getting these. All right, so check out what I was seeing right here earlier. What I was doing earlier was saying like that was about my closest one, and I felt bad because it was like super, super close over here. And I was like, they almost match. They're like really close, but they're clearly off. You guys should recognize 1.57. That's pi over 2. And it looks like if I do that shift, it looks like our two constants of integration are actually differing by pi halves right there. So this is my crazy, crazy way to tell you. I knew I was going to come up with why these were actually the same here. I knew I didn't make this. Yeah, I got to change the bounds and not just the step size. I could totally. Oh, it's probably not down with the very narrow bounds if my step is out there. So I bet you're right. I bet if I made it like 1.5 to 1.6, it would be cooler with me doing like the 1/1000s out there. But also, kind of what happened there is I used my math sense to be like, oh crap, I'm getting 1.57. 1.57 means I'm actually thinking about pi halves, and it turns out that I actually was right there. So check this out. These are the same graph as each other unbelievably. And man, like literally, I don't even believe this, but I'm looking at the freaking graph right there. These two wildly different functions, one with a sine inverse, one with a tangent inverse of all this crazy square root stuff, are literally equal to each other. I have no way of guessing or verifying that these things are actually the same, but we just showed, and all I'm going to do to be good with my answer here is I'm just going to call this like a, C1 instead of just C right there. And we're good. So like, how wildly unlikely is that? And the answer is, I guess, very. But the point is that these two things are actually equal to each other, and we couldn't ever come up with a way to prove that. Like if you were to ever come up with the actual algebra or trig that shows that those are equal, you get the gold star for the week because that's unreasonable to show right there that they're equal up to a shift that C equals C1 plus pi halves or something like that. So again, holy cow, I really hope you don't choose this route right here to do this problem, but like, if you don't see the conjugate, you got to do something. So as my highlight on the way out the door right here, realize that sometimes it's really helpful for you to do a lot of manipulation with just a simple old u sub. I made a u sub here of the literal entire integrand, which seems like a ridiculous move to do. I didn't want to find du from my u sub, so I just didn't. I know that I've learned the lesson in this chapter that defining a u sub and then immediately resolving it backwards in terms of x is sometimes valuable. And in fact, Literally, the way that we define our trig subs is the same backwards type of sub. We actually make their substitution for x instead of defining the new variable, right? Instead of doing u equals, you do x equals. It went backwards. And honestly, didn't we even do this another one that was like this before today too? Or am I just thinking of other problems out there where we sort of like, oh, I guess in this one, no, but that was for the other one out there. But still, like this does happen where we kind of like resolve back the other direction for our pieces that we're looking for. So in this one here, I think that I was just thinking of here where we had to solve x for u to get back into the sine inverse right there. So again, here I just said, nope, not finding du, not doing it, not interested, but I can find x in terms of du, and then I can use this to find what dx would be. This wasn't the grossest expression ever, and this was a good expression because it didn't involve a radical. Like that was really my big bugger of this initial expression was what do we do with this whole thing being underneath the square root? Well, at least doing this got us out from underneath the square root. So again, it wasn't clear to me that that was useful, but it did seem better to get us in terms of a rational function instead of a root function. So I followed my advice from the book or from the strategies, which said if you have a radical expression, maybe just u sub the whole radical expression, and I did it. Then the book said if you have a rational function, use partial fraction decomposition to break it down, so I did it. Then the book strategy said if you know the antiderivative, do it. If it's one that we've seen before, because the book has done this one before, then use previously known results, so I did that. Then we want to sub back in to get back into our old situation, simplify. And if you see results that don't, oh my gosh, I've been sitting here on my wrong thing this whole time as I've been talking through all this stuff. What's wrong with me? Of course, I go and botch it at the end right here. I've been sitting here trying to talk through this problem. I'm going to go ahead and repeat my words right now just because I want to kind of wrap this problem up. I defined my u based on the book's recommendation of saying if you have a whole radical expression, sub the whole thing for u. Doing du seemed stupid to me because I was going to have to do a chain rule with a quotient rule, didn't want to do that. So instead, I've learned this lesson that sometimes immediately after making your u, it maybe is worth it to reverse solve for the other variable for x, so I did that. This is what's helping me say, and doing these kind of like intermediary substitutions where we don't do all of the subbing right there. I said, listen, all I need is dx, and I know that I can get dx if I find x and take its derivative. So I found x and I took its derivative, got an answer in terms of du. And again, not clear that this is a great thing for me to deal with, but it is clear that we have exited the situation of being within a full radical, which was a problem for us. So the book told me if it's a full radical expression, u sub the whole radical expression, and that worked. It got me to a rational. The book said if you get to a rational, do partial fraction decomposition and rip it up into rationals. In particular, it helps to have numerators that are constants instead of numerators that are like u squared up there. The book then says if you know your antiderivative, just do it. We knew the tangent inverse one. The book also says if you have previously seen the result, reuse it. And the book has previously done this one in its examples, so I reused it. Then I just simplified my answer and got down to a gross expression. Don't mistrust yourself. The back of the book would be telling you certainly that much easier expression for this one, but maybe you didn't see that go the conjugate route and you did this. Don't just think that you're wrong. Go to Desmos, go to Wolfram Alpha, graph some things, say are these equal to Wolfram Alpha, and it turns out that these literally are equivalent expressions right here, which I just got to say, there's just no way that we are interested, even if we could do the work, interested in doing the work to prove that these are equal. But it's really sweet to see that we're taking like such different routes to get there that have nothing in common with the ideas or the trajectory to get there. Our answers look nothing the same, but I hope that you've learned from trig in your life to trust that just because two answers don't look the same doesn't mean that they aren't the same. And right here is a incredibly good example of that. So I'm surprised with myself that I only chose to do the examples that the book laid out instead of like picking out other homework problems here, but I do think that these encapsulate every single idea that we're interested in talking about today and in using like our step-by-step guide. Like I don't think it's unreasonable for you to approach difficult integrals by just going through this step list, checklist right here and saying, okay, should I algebraically manipulate? Do I have trig stuff? Should I try u sub? Should I classify it? Should I try these trig subs? Should I try these partial fraction decompositions? Should I try integration by parts? Are there problems that we've seen before? Like, go down the line right here. Ask yourself all these questions. This list kind of got us through everything we needed to say today, needed to see today. And again, I really picked these examples here to emphasize to you there's lots of different ways. And so therefore, I like to also think that rather than try again, I think that keep trying the same thing in a sense is worth it. It was very unclear in this second example that we were going in the right direction, right? Very unclear that any of the work that we were doing mattered. I couldn't tell that anything was a smart move here until I literally got to this expression. I did a whole page of work before I got to something where I was like, holy crap, I think we're actually going to be able to finish this. That didn't happen until I was right here. So like, keep going. Don't get discouraged. Keep trying to make different manipulations happen so you can fight this thing into a corner where you recognize it and can handle going the rest of the way. And even once you get there, use graphs, use technology to confirm that your answer is right, because it is highly unobvious that this is the truly correct answer right there. But technology helped me confirm that it was. So I thoroughly enjoyed this problem here. The good part is that the book says, by the way, you could do this one if you just subbed out u for the whole radical expression, but it's gross. And so immediately, obviously, my thought was like, well, I'm obviously doing that one then. And I think that there's value in doing these, even though it's not the best way. It's good to see that, like, if you really are carrying your algebra beating stick with you, then you can do anything. And so, it's maybe not nice to think of algebra as a beating stick. Maybe we could go with something more positive and less violent than that. But like, a lot of these things will resist your attempts to manipulate them meaningfully, and you need to force them to be manipulated because you have to be that confident in your algebra and your trig. So that's what I've got for you for 7.5 as my ending. Again, I'm going to say what's above me right here. We're going to take our first test next week. The test is going to go up through section 7.5. Next Monday, I am going to talk 7.7. We're going to completely skip 7.6 anyway, because 7.6 is like, how do you use a computer to calculate integrals? And the answer is you go to wolframalpha.com. So that's 7.6 right there. We're going to talk 7.7 estimating integrals, 7.8 indefinite integrals, and integrals with bounds of infinity. Those are going to be super important for us for a bunch of the stuff that's coming up here. Integrals with bounds of infinity come up in a significant number of places. So those will be really important. But those topics are kind of a little bit different than a true technique of integration. It's really just like how to handle other things that you see integral wise. So this is a very good chop point halfway through a semester right here. So your tests next week will cover up through 7.5. I am going to cover 7.7 next week before you take your test, but no 7.7 stuff will be on the test. I still haven't exactly decided exactly time-wise what I want the test to be, but I am thinking that I'm going to do the same thing that I'm doing for my stats class this week, which is that it'll just be like noon on Wednesday to noon on Friday being like your available window of time. I am also, in a sense, like slightly reducing the amount of homework to be done associated with this week of the class and next week of the class because you've got the test, and I do want everybody to like not do anything else other than the test for the 48 hours in which it's available. You shouldn't be thinking about other things at that time. So we'll do that. You'll certainly be getting information from me by the end of this week about finalizing the details about the test. And then next week in the week 7 module in Canvas, there will be a little section in the module that will say like your test will appear here on Wednesday at noon. And then at Wednesday at noon, you'll be able to click it and get in there and get the test and stuff like that. So just keep your eyes out on Canvas. Keep remembering that it's there. You should be thinking things to yourself like it is in your best interest to be 100% done with everything up through 7.7 before you take the test, since obviously I expect you to actually know all that. So I think what you should be thinking right now is you need to be done with like everything that we've covered in this course by like Monday of this coming week. So you can maybe take a gander at 7.6 on Tuesday, take the test Wednesday through Friday, and then handle your like half week of content maybe on the weekend or something like that associated with 7.6 is what I'm thinking. So good. I'm glad that we had some good comment and chat here. Plus we got people, I think our extras in chat. It was a good sevens pyramid right there. That was a good one. So I will see you guys next week. Hit me up with questions as usual. I got your My Open Math homework posted last night, which I think, and I'm going to post some recommended problems from 7.5 for homework that I'm not going to collect. So I think that this week there will just be a My Open Math homework and a weekly writing, and that's it. I will assign some other problems, and you really should do them because in my mind that's basically like your test review. Is basically 7.5 is the test review. So I'm going to assign them but not collect them. So the only thing you have to turn in for this week's content is just My Open Math for 7.4 and your weekly writing, and those things are posted in Canvas there. So thanks to you guys in chat today, and I will see you guys later this week or next week. Have a good one.